Welcome. Are you hoping to get that ideal score, the 528 on test day? If so, you're going to need real mastery of the basic concepts that are tested on the MCAT. In today's lesson, we're going to dive into some of that content with a thorough review of ideal gases. In this lesson, we're going to take a look at the ideal gas law itself and what it can tell us about relationships between different variables. Then we're going to explore an example and really take a look at how a gas may deviate from ideal behavior. And of course, we're going to see how critical thinking might save the day in a non-ideal gas situation. Go ahead and read through the scenario in your lesson book. You probably recognize the compound nitrous oxide. It's laughing gas. So there's a good chance you've had a real-life experience with this stuff while you were at the dentist. In fact, you may have even noticed that the mask you wore that day was hooked up to a metallic cylinder, just like what the scenario describes. So there's a very real-world application of anesthetic gases, and when they don't behave in an ideal way, that could cause a real problem. Imagine your doctor tried to calculate how much nitrous oxide they were giving you based on the ideal gas law, without accounting for the idea that they aren't using an ideal gas. You could get a dose far higher or lower than the physician intended, and that could spell real trouble. So we're going to take a stab at how a gas should behave ideally, what nitrous oxide does differently, and how those differences can be compensated for in real life. You probably know the ideal gas law already. It's PV equals nRT, where P is pressure, V is volume, N is number of moles, R is a constant, called the gas constant, and T is temperature. This equation is actually a combination of several relationships between variables, and if we analyze it properly, it'll give us a ton of information we can use when solving MCAT problems. The prompt asks what we can determine about the relationships of the three variables P, V, and T in terms of their relationship with N. Note that I didn't ask about R. Why not? R is a constant. No matter what you do to the other variables in the equation, you can't possibly change R. This may seem like a little bit of a pedantic point to make, but recognizing when variables are and are not set values is going to be a huge skill for testing. If we set the entire equation equal to N, it'll be easier to spot all of the relationships of the non-static variables to N. Now think through the relationships of P, V, and T with N, and write them down in your lesson book. Okay, let's take a look. P is in the numerator when set equal to N, which means those two are proportional. As N goes up, if the other variables don't change, P goes up. V shares this same relationship with N, meaning V and N are also proportional. The one variable with a different relationship is T. Because T is in the denominator, we know 1 over T is proportional to N, so T and N are inversely proportional. As N goes up, T would go down based on this relationship. I was really careful with my phrasing here. Why was it that I always said it was N changing, causing a change in the other variables? Why can't I say, for example, that changing pressure will change N? Well, as we said, N is moles of gas, which is a constant for a given system. You're not just going to make more gas molecules by increasing pressure. If it was that easy to create matter, we'd be doing some really crazy science right now. N's inability to change actually brings us back to the reason I asked the question about the gas constant. Even if a variable isn't a true constant, you do need to recognize what variables are able to change and what variables are not able to change in a given system. In fact, this is where mathematicians get the terms independent and dependent variables. The number of moles of gas is mathematically the independent variable, and the pressure or the temperature or the volume each depend on how many molecules of gas are present in the first place. Now, we're going to explore those same variable relationships in a little bit more depth. This prompt has us looking at the relationships between our three changeable variables within a system: pressure, volume, and temperature. Specifically, we're asked to consider these variables using Boyle's and Charles's laws. First, just to demonstrate your comfort with the material, go ahead and draw in those graphs if you've already memorized them. At this point in your prep, it's likely you've seen these figures before and you know them by heart. But it's still important that you know what they mean and how they're generated. So we'll start with Boyle's law. Notice how Boyle's law officially says P and V are equal to some constant, K. Based on the ideal gas law, what does this constant K have to be equal to? Well, If you know your Boyle's law, you know that it dictates the relationship between P and V only when T is held constant. So if T is held constant, that value K is equal to N, R, and T, the other three variables in the ideal gas equation. Now, if we solve for P or V, we should find that they share an inverse relationship, which is where that curve you drew in earlier actually came from. If the temperature isn't changing, as P goes up, V goes down, and vice versa. This will prove important not only for ideal gas law itself, but also for your understanding of thermodynamics materials. Now let's consider Charles's law. Is K equal to the same thing here? No, it can't be. Charles's law is about temperature, so T can't be held constant. Instead, in Charles's law, it must be the pressure that's held constant, which means this K is equal to NR over P. That's why there's a small k in these equations, rather than some set variable. The lowercase k is commonly used to mean some constant value k, but it doesn't mean that the same value will be held for k from one equation to the next. Make sure you're careful about this going forward. At this point, if you solved for v or t, you should see that these two variables are directly related, which is why Charles's law is drawn as that stereotypical straight line. As v goes up, T goes up, and vice versa. Now it's time to test your skills on your own. What's the relationship between pressure and temperature? You would want to apply the same logic we did before, as in hold the third variable constant. In this case, the constant variable needs to be volume. That means our overall constant K is equal to NR over V. And if we plug that into the original ideal gas equation, it gives us P is equal to KT. In other words, just like Charles's law, pressure and temperature have a direct relationship. We would expect their graph to be another straight line. Now that you're a little bit more comfortable with how an ideal gas should behave in a system with set values, it's time to explore just what's different about nitrous oxide. We are going to compare N2O to one of the most ideally behaved gases in existence, helium. If we really wanted to see how these two gases differ in behavior, we would want to hold a few things constant. If they were held in the same type of environment, at atmospheric pressure, so same volume, pressure, and temperature, and in the same amount, same N, they should be exactly alike. However, they're not. There are two differences clearly visible between these two gases in these visualized containers. What are they? There are two big differences visible here. The little N2O molecules are clearly a different size in that they're much bigger than the helium particles. And also, the N2O molecules displayed a polarity, which the helium molecules didn't. Let's start by thinking about size. If we look at the two containers, container 1 clearly has more space. This may seem like a simple observation, but it actually has pretty important implications. Normally, when you're using the ideal gas equation, there's only one thing affecting volume or pressure, the size of the container itself. Now, though, the molecule is actually taking up non-negligible amounts of space. We can imagine this would definitely affect overall volume measurements and pressure measurements as well. If you shove 5 beach balls into a container as compared to 5 ping pong balls, the space taken up by the beach balls is going to make a huge difference to the system. The volume of the container would no longer be accurate because too much space is being taken up by the balls themselves, and likewise, the pressure would no longer be accurate. How about the other difference, polarity? To explore this, let's think about a collision. If a helium molecule bumps into another helium molecule in container 1, we know that they should just bounce right off of one another. With no real charge interaction, the helium will continue to move totally freely. However, if nitrous oxide is brought close to another nitrous oxide molecule, what might they do? Well, we can imagine a magnet here. If you bring two magnets of the same charge type near each other, they'll repel. However, if one of the magnets can spin and line up in such a way that its positive pole is facing the negative pole of another magnet, bam, we're sticky. There's an interaction like this available when a nitrous oxide molecule strikes another nitrous oxide molecule, and if that interaction occurs, the molecules will experience a charge interaction that will lead to increased stickiness between them. This means the molecules may well stay closer to one another than would be expected in an ideal gas, meaning the estimated pressure value for the gas pressing on the container would be lower than it should be. So for both size and for polarity, N2O is not going to behave ideally, and the ideal gas equation itself doesn't have the means to compensate for those deviations. Acknowledging the problem caused by non-ideal gases is one thing, but actually fixing the problem is another. I want you to take a look at this final prompt and try to answer it for yourself. How would you expect N2O to behave in the storage type described in the scenario? Well, let's think about what would happen as you added more and more nitrous oxide to a pressurized, cool, small container like this. At first, gas particles would be spaced out like normal, but as you add more and more gas, nitrous oxide molecules will be forced into close proximity and will have to try to align to minimize negative-negative or positive-positive charge interactions. At this point, the molecules are far more ordered than they were when we had a big open container, with lower entropy. And with that cool temperature and tight space, conditions are perfect for a phase change. Ultimately, the medical profession has actually used the non-ideal gas behavior of N2O to its advantage. The fact that N2O at high pressures behaves so non-ideally as to become a liquid actually makes it easier to store and dose N2O. That's absolutely key to dosage, because now, rather than the doctor doing something crazy hard, like using the van der Waals equation of state, the doctor can now calculate how much N2O to use with a simpler measure, like molarity. So, rather than using tough equations or trying to guess correct dosages, current medicine has worked its way around this problem in a more critical thinking way, by recognizing that the way a compound is stored doesn't have to be the same form as the way that it's ultimately going to be used. The kind of critical thinking that nitrous oxide canister inventors used is exactly the kind of critical thinking that you're going to want to use on test day. In this lesson, we got to look at ideal gas law with a few of its applications, as well as a situation where ideal gas law didn't apply, and how, at least conceptually, we can deal with a non-ideal gas. Before test day, make sure to get some practice, both applying the ideal gas law and identifying situations where it doesn't necessarily apply. See you next time.